say this. Yerevan, make some noise! Woo-hoo-hoo! Even if you need to put down your phone to make some noise. Who here was born in the year 2000? Or later? Thank you. Thank you. The last patch to a MySQL database was made by Konstantin Osipov. The MySQL in the year 2000, the version was 3.23. If it makes sense to you, this is your guest star speaker that has 40 minutes on the stage.
У меня есть свой микрофон.
Kostashki!
Hey, nice mix of English, Armenian, and Russian here. And okay, I will give a bit different introduction of myself. Indeed, the first patch I made in the year 2000. I'm not that old. It's not the last patch. Okay, here I'm speaking about a topic that's interests me personally. So it's a while ago I made a prediction that NoSQL will start supporting transactions widely. So more and more SQL databases will be supporting transactions. And this prophecy, this prediction, it comes true now. So here's how this talk was born. But first, just a few words about myself. I've been involved with databases for a while, indeed. And right now I'm with ScyllaDB. It's a NoSQL database. It's a Cassandra-compatible NoSQL database, which is much, much faster. It utilizes the shard per core design, where a single core has a single shard, owns a single shard. And this is a very similar design to Tarantul, which I started working on more than 10 years ago. So it's also shard per core NoSQL, but in memory. So Scylla is for like petabyte scale volumes. And I am also founder of a company which is called Pico Data. It's like there's a Teradata and there's Pico Data. Like Pico is -12, Tera is +12. So that's a joke about how big the databases have become. And so this work has been done in scope of this startup that I founded. And the idea, how it all came about, like there is this card processing company which ships card processing software all around the world, and they are currently, of course, working on Oracle database. And they said, hey, we found this funny, interesting database which we would like to use as a substitute for Oracle. Could you check it for us, whether it's good at all, whether it's not losing data, whether it's good for transaction processing, and so on. So they wanted to switch from Oracle to transactional NoSQL for card processing. That's the business case, how it all came about. And when we started looking at that from like different angles, why would you do that? Why vendors like NoSQL vendors start supporting transactions? What is a viable use case? Because you can have a feature but have no use for it. And by the way, feel free to stop me anytime. Feel free to interrupt me. It's even funnier. So this is just how I usually deliver my talks. You can stop. You can raise a hand, and that's fine. Okay. So they said. So just check this. So why they would want this? And there are many databases around, and banks are pretty conservative and pretty stingy. Let me put it this way. So they know how to count their money, and they know that Oracle so far has been cheaper for them. But going forward, there is this. There's this, of course, this vertically scaled on-premise databases. There are horizontally scaled cloud databases, and there is the third wave that we are now approaching. The wave of horizontally scaled on-premise serverless databases like Kubernetes, KubeOps, You don't have any ops team. It is very elastic, so you can add more compute and you have more throughput of the database. So that's the way we are approaching, and the cloud is just a step towards this. Because if you look at the cloud, what the cloud does for you, it saves you some ops. You don't have to pay for a DBA, but you still have the DBA. It's just behind the curtain. So there's this new wave, and there's this fun idea, like, could we just have a Kubernetes cloud, a NoSQL database, we just throw resources at it, we don't need to manage it, like heavily manage it, and it's reliable, it's scalable for us. So that's the idea how this test came about. And if you look at, indeed, how NoSQL market came about, okay, no laser tagging, okay. So I will just use my hands. So if you look at how NoSQL market started adding transactions, you'll see that first of all, cloud vendors started having it, like Fauna, like Cosmos, like DynamoDB. These would be the first NoSQL databases which support transactions. And then more like you can download and install kind of databases started adding it, like Couchbase, FoundationDB, TiDB, and so on. MongoDB, even though MongoDB is now a largely cloud vendor. So, and then there's another question, like you have this test, how would you check that this database fulfills these criteria? And let me remind you, there are two criteria. First, it got to be ACID, and second, it got to be like scalable. It got to be NoSQL kind of scalable. You throw more shards at it, and it scales the workload. How do we check that? And there are, of course, tests like Jepson, which would check that the database is ACID, but it's not. By the way, everybody understand what ACID means here? Yeah, okay. So, but Jepson doesn't check performance for you. It's like, you know, it throws maybe 1,000 queries per second at the database. It doesn't really scale well. So, and besides, when it checks the ACID properties, it doesn't check the manageability properties really. So it's not really a test. It's not really a criteria. Like if you compare Jepson with TPCH, for example, TPCH is like a database warehouse test which would give you some numbers in a specific workload. Jepson is like a bunch of building blocks which you could use to build a test you like. So it cannot serve as an objective criteria because in the end you apply it. You use your methodology to check that the database is ACID. So we needed a test which would have performance, which you have the same methodology for all of the databases, and which would have some nemesis in it. So like some failures, like nodes going down, network going down, which we could apply while running the test and find out that the database actually survives, that no transaction is lost. So this is how this project came about. This is its website. At this point, we support 5 vendors. It's PostgreSQL to begin with. I will explain why we needed PostgreSQL, even though it's not a NoSQL database. It's CockroachDB, MongoDB, FoundationDB, and Yandex database. And I'll briefly talk about all of them in this test, in this talk. So these are our test subjects. And now to give you an idea how we were able to achieve that, that goal, actually 2 goals. There is this, it all came, first I got familiar with this like about 5 or 7 years ago when there was this large Russian bank. They started looking at in-memory technology as a substitute for Oracle, and they came up with this test. It's called the banking test. And then at Scylla days, Scylla supports actually a thing called lightweight transactions, like Cassandra. Anyone familiar with Cassandra here? Okay, nice you're listening to me, so thanks for understanding. So Cassandra has this lightweight transactions thing that is not the real transactions really, and they're not really lightweight. And they call them lightweight because they thought that like if you don't have real transactions, that what would be a good name for like non-real transactions? Let's call them lightweight. They're not really lightweight. They use paxes under the hood. They're really hard to use, but still they allow you some linearizability to code some linearizability workload. So first, this test was implemented for like Sberbank in Russia. Then I implemented it for Scylla using lightweight transactions. And the idea of this test, why it's like so versatile, you don't really have small transactions like there is, for example, Hermitage test for ACID properties, and it has just really tiny transactions. And you don't check individual transactions. What you do is you generate a bunch of accounts, bank accounts, like big bank identification number, bank account number, BAN. So every account is identified with 2 numbers. Then you simulate transfers between these accounts. So you just withdrawals, deposits, transfers, and then at the end of the workload you check the total balance. The total balance should never change, should never lose money, right? If you send money to someone, the someone gets that money, and you withdraw that money from your account, but the total stays the same. So the way this test works is that it generates, pre-fills the data, calculates the total balance, runs the workload, calculates the total balance again, compares, and if the results are the same, then we assume that this is a correct database. It's not, a hard written, like it's not in stone, this assumption, but it gives you a pretty good estimate. Like especially if you do what I said, you do Nemesis in a parallel. You drop the nodes, you stop network between some of the nodes, you partition the network between, like, you try to have a split brain, you skew time and so on. So you inject some failures into the environment while you're running this test. This is how it can tell you whether a database is getting good. And also, another important point that, and I'll talk about it more a bit later, is that did you ever have see like let me show you this slide. Did you ever deal, when you deal with the money, has it ever been even? Like there is a even distribution, there is normal distribution, there is Zipfen distribution. What's the distribution of money? It's never fair, right? So whenever you deal with the money, you deal with some skewed distribution. Some have more, some have less, and this is the database workload. So if you think about this, this is fundamentally contrary to the idea of horizontal scalability. You cannot, if your workload is just touches a few accounts, and you want to scale this workload horizontally, how do you scale these few accounts across 1,000 nodes? So this is fundamentally contradictory. And the good part about the benchmark is that it has different distribution support. So you can actually play with it. You can say, hey, let's simulate payroll. Imagine a very large company, it has like 300,000 employees, and we want to simulate a payroll. We just, it's a salary day, we want to pay salary to everyone. So it's like 300,000 transactions running as a batch, withdrawing money from a single account and depositing money on a bunch of other accounts. So this single account becomes very, very hot. So, and then the next question, why did we start looking at PostgreSQL as one of our test subjects? And the answer here is that it's an excellent measuring stick. So PostgreSQL is a vertically scaled database, and in PostgreSQL, if it works worse than PostgreSQL, why would you do that, right? Why would you start using a NoSQL database which has less features, which is less common, if it's just worse? So to give you a more specific idea how it, like the schema looks like at PostgreSQL, this is the schema definition. As you can see, it's a pretty straightforward schema, right? So you have this accounts table, and you also have the transfers table. This is how the transaction looks like. Well, the real world transaction is a bit more complicated. I'm just giving you the idea. So you withdraw and you deposit, right? So PostgreSQL was our first test subject, and that another idea of the test, like you want to play with the numbers. So you want to have cloud hardware and run it on a few cores, run it on multiple cores, run it on a few machines, run it on many machines, change the disks, change the RAM. So we use 2 cloud providers, unfortunately, Oracle doesn't disclose its numbers, like what are the frequency of the CPU. We could look at that, of course, but you know it can change. It's not settled in paper, so there's no point in putting them here. But this is the hardware we used at Yandex. And I'm jumping ahead of myself. This hardware has also changed because when we started testing Yandex database, we actually upgraded the hardware quite a bit. But to give you an idea, why cloud is also important in this test. When you look at the cloud storage, you can have an attached storage, or you can have a network attached storage. You can have local or network attached storage. So the difference would be that a network storage is actually very resilient, very elastic when it comes to IOPS. So a local storage can have some differences in IOPS depending on how you write this. So if you write with large chunks, it's going to be as scalable probably. If you write with small chunks or with small chunks, local storage can have a different throughput. Also, local storage is impacted by read and write coexistence. Like if you look at the log structured merge trees, like Foundation DB, for example, uses RocksDB under the hood now. So when these databases they start compaction, they actually increase the utilization of the bandwidth of the disk. So you don't notice it if you use network attached storage. And so this is why this is important. So we try to use local disks, preferred local disks, to just avoid its effects, to create fair conditions for everyone. And the good part about it is that, like I said, we were able to play with different setups. Like Stropy, it's written in Go. It uses Kubernetes, and you can just tell it how many cores, what is the structure of the test, how it should look like. It has 3 tests, like small, medium, and large. You define how many counts, how many transfers you want to have, and you give it some hardware, then you run it, and you just get the numbers back. So these are PostgreSQL results, and we actually tuned every database. So it's not like we take a stock database and use it, because when you take a stock database, it's not guaranteed to perform optimally. Some stock configurations, they could just be built for, you know, tutorials, like download and play. So we tuned every database. We tuned PostgreSQL. We used PostgreSQL 13. The PostgreSQL tests were run like this last year. This is actually a very long project. We started in year 2021, and now we are approaching in start of 2021. 5 databases, like every database actually takes 3 to 6 months to develop this. If you think about how the differences between the database, what Stropy allows you to do, it has this abstraction layer which doesn't depend on specific SQL dialect, on the API. So for example, Foundation DB, it doesn't support SQL at all. It doesn't support secondary keys. So you have to write this all by hand to support this database. But it's still interesting to look at the core functionality, how transactions perform. So, and with Postgres, we have PG bouncer. We tuned a bunch of parameters. I now will not like go into what these are, but we used some pretty well-recognized consultants on the market to help us, because, well, I do have some familiarity with the current PostgreSQL ecosystem. So I just asked a friend who happens to run a company, who happens to have a lot of, you know, PostgreSQL consultants in it. So, but the main tuning parameter, if you go back to this SQL, the main change we had to do to make PostgreSQL perform is change the order of transactions. So if you think about withdrawals or deposits, you naturally create with your transactions a deadlock situation. When you transfer money from one account and deposit it to another account, and another transaction concurrently transfers money from that account to that account, or possibly there is like three transactions. There is a loop. Anyway, you have a dependency loop between transactions. So they can look this way, or there can be 3 transactions. Then they look at each other. This creates a deadlock situation for the Postgres deadlock detector. And in the end, it's not just bad that this transaction rolls back. it's bet that the client stalls for the deadlock detection timeout while this transaction is waiting. So what we actually changed, the main parameter that improved PostgreSQL performance was to order the transactions, order the statements in the transaction by the bank account. So lexicographically, first bank account always comes first. This is how you naturally avoid deadlocks. If you have a conflict, the transactions just wait for each other and then they both commit. So this is how we got to these numbers. And well, the good part about it, if you look at this, and you, by the way, multiply everything here, but at least a factor of 3, because I'm not counting replicas here. So you have 10 cores, you have 160 gigabytes of RAM, and you have 6,000 transfers per second. So that's the numbers you get. And these are actually pretty good numbers. If you look at most of the banking, say in the, well, I'm looking at Russia, probably in the United States or like in Indonesia where there are more people, the workload can be, like the peak rate can be higher. But in Russia, the peak rate for like Sberbank, it's about 2 to 3, like Christmas sale. It's going to be 2 to 3,000 transactions per second, and maybe up to 5,000. So technically, PostgreSQL can handle as large bank as Sberbank if you do it properly, right? So, and these are just a few cores. You can throw more cores at Postgres. You can throw 100 cores at Postgres. But of course, it stops somewhere. Like around the 100 cores, you already don't get as good numbers. It doesn't scale with an increased number of cores. So, and if you look at where the limits are, I mean, one thing I have a friend who always says that unless you can explain a benchmark, it's not a benchmark, it's benchmarketing. So you have to explain what's going on. Why would we stop at like 5 or 6,000? So PostgreSQL was heavily I/O bound, and this I/O comes from both replication, because if you turn off replication, you have higher throughput, and from secondary keys maintenance, so the object storage underneath. So if you could improve PostgreSQL object storage, you could improve the throughput of that as well. And I know that there are currently like projects which are improving the storage of PostgreSQL, like ScyllaDB is improving it. And I'm pretty sure like going forward, the situation in the upstream and the trunk will also improve. So this is not the end of the Postgres story. Now the next database is like our main test subject is FoundationDB. So Foundation, when you look at different databases, you like say, hey, was this database built for transactions? Was MongoDB built for transactions? Was CockroachDB built for? So some databases are built for transactions from start because the founders, they like define their market niche as a transactional database. Others like Mongo, they just added them later. And you will see the difference in this slides in my talk, how that matters. So if a database was built for transactions from day one, like Foundation, it usually fares better than a database that's added it on the side. And Foundation has a very specific, it's a very early architecture. Like currently, the distributed transaction algorithm, they develop like year by year. So just a recent year, there was this very good Accord paper which shows how to run completely distributed transactions on using Paxos under the hood, which really scales well, which really avoids deadlocks and so on. So Foundation started when we had nothing like that. Foundation started even at the times when distributed serializable snapshot isolation was not published. And just serializable snapshot isolation paper probably came out in the same year when Foundation was founded. But still, when you look at the design of Foundation, you will see, and they say that themselves, like if you look at the paper, you look at how they describe their design, it's very similar to the implementation of distributed snapshot isolation. So I have another story is that if you look at distributed algorithms themselves, again, then there are like, in principle, there are like two branches of this. One of them are centralized in one way or another. They have a central bottleneck eventually, and another are completely distributed. So Foundation uses a centralized in the end. So like think about this. It's a distributed database with a centralized transaction control. So in the end, there is like a single point of, it's not a failure, it's a single throughput limitation point, which would resolve transactions which impact many partitions, many keys. But the way they handle it is that they actually shard it to the, like small transactions have a very good chance of running concurrently using concurrent resolvers. They have this concept called resolver. They actually, the way you commit transactions in Foundation, you first get the sequence number for it, then you send it to a resolver, which resolves the conflicts, then you send it, it's all role-based. So on Foundation, even though it looks homogeneous to you when you install it, like you can install it as many cores as you like, in the end, under the hood, it runs multiple roles. So there is the sequencer role, there is a resolver role, and then there is a log storage role. After you pass all the 3 steps, you apply it to the main storage, to the database. So this is how they achieve high throughput. And I'd say it's quite a nice database, like in the way it runs, it operates. You will see the numbers here. You can see that we ran, like here it's just a snapshot of we were running. We were running hundreds of tests, and here we just select the best. So the best test is, if you look at this, it's like 20 machines, and it gives you 10,000 transactions per second, around 11-ish. And in the end, you want to sort of calculate the cost, right? So if you just give me a second. If you look at how many transactions per second you can get from the same hardware, look at Postgres, look at Mongo, you will see that it's actually giving you pretty decent numbers, right? So these are numbers there. Even though it's a distributed database, it gives you numbers which are better than Postgres numbers. The main contribution to this improvement is coming actually from the storage level. So it's quite, I quite believe that Postgres can give the same numbers if its storage level improves. Because when you look then at the, I understand you cannot make any sense of this, so I'm just showing it for your, like, if you look at these small titles and so on. So, but just to give you an idea, like CPU utilization here is like 40%. I'm not allowed to leave that corner. So sorry. So there is the camera there, but so I'm not allowed. So I will just show it from here. And CPU utilization here is like 40%. I/O bandwidth is lower as well, and so on. So you consistently see lower utilization, lower bandwidth, even though you can. So this is how it gets to higher numbers, because you know, the basic queuing theory, if you just congest your resources, you start running slower. So, and another thing to note is, like, remember in the beginning of the talk I said, is there such a thing as horizontal scalability? There isn't. If you look at how Foundation scales as you add cores to it, you will see that the curve is actually not linear. It's actually bending. And especially interesting, like at 10 cores, you get around 7-ish. And at 20 cores, you double, and you would expect you would get like 15 or 16,000 transactions per second. But you only get 11. So I'd expect that curve will get flat at around like 60 cores, 80 cores. This also raises a question, if like PostgreSQL, or like not just PostgreSQL, you know, MySQL, other vertically scaled databases, they can scale up to 60 or 80 cores. Why would you do that? Like, why would you use a horizontally scaled database? Foundation doesn't have secondary keys, it doesn't have SQL, doesn't have constraints, doesn't have stored procedures, nothing. It's just a key value store with transactions. And why would you use that? So remember that premise. There's a very important idea where you can have zero ops. It's a very lucrative idea. This is why we are looking at that. So that's Foundation, and basically we could stop here, because comparing these two just gives you the main idea of what I was trying to deliver with this talk. Like, there is no holy grail of horizontal scalability when it comes to transactions. Some fare better, some fare worse. But let's look at other numbers as well. MongoDB. MongoDB scalability, I mean, it's an easy target, but we did the fair job of every time we test a database, we actually try to get in touch with the vendor. It's not like we are picking something, tweaking, and then publish the numbers. We sent the report, we got in touch with them, they just decided not to respond. So, of course, you could say, hey, these guys are from Moscow, they're probably Nazis, why talk with them? So, but no, they just were very quiet. But if you look at MongoDB architecture, so it's you know that MongoDB is partitioned is like initially it wasn't distributed database. Initially it wasn't. It was just like MySQL. It had replication. It had no transactions on a local partition. So the main thing in MongoDB was this thing called oplog, and later they started supporting transactions as they added WireTiger storage. So if you look at the design for this, like for example, some database they use the transaction log to replicate. Some maintain two separate logs, one for write-ahead log and another for replication. But in Mongo, we have essentially three layers. We have the WireTiger log, which supports local transactions. We have replication log, which supports transactions within a replica set. And then we have a separate algorithm on top of that. And MongoDB is actually very, publicly, I wasn't able to find any papers where they would describe their transaction algorithm. But in one paper, I found that they actually use plain good old two-phase commit, which doesn't have liveness properties, to run transactions across multiple replicas. So that's the third layer they use. And but first, we started to look at how MongoDB fares vertically, because vertically, it gives you a good measure of how it's going to scale horizontally. So you take the same resources, you put at it 12 cores, and again, 12 cores is actually much more here than the other 12 cores that I mentioned earlier, because it's 12 cores per shard. And you need to have 3 replicas of this. It's a single shard install. So you have in total you have 36 cores and 120 gigabytes of RAM. So you have around 3,000 transactions per second. This is how you scale vertically, but at least it shows some scalability, right? So you put more hardware to it, you get better numbers. And then what I call horizontal scalability of MongoDB. And so it actually gets worse as you add hardware to it. So that's like, I mean, yeah, and I just explained why. Because it is running this really leveled protocol for supporting multi-partition transactions. So you can expect there is a lot of coordination going on. Probably 4 to 8 network messages are passing before it actually can commit. I don't know, I mean, and just to say, we are not experts in every database. I've spent, I started my career as a MySQL contributor back in the 2000s. Then I did another database, and now I'm with Scylla. So I've been doing databases for my entire career. But I cannot claim I'm an expert in every product. But we did get in touch with Percona to tune us. So Percona is a fairly good, recognized member of the database community. They support MongoDB. They have experts on MongoDB. So it's a tuned setup. And we tried MongoDB 4, MongoDB 5. Probably they will improve it over the years, maybe in the next release. But these are the numbers. So, and if you look at this from the TPS per core, from the cost perspective, you will see that Mongo fares the worst. I remember Oleg Bartunov on stage in Novosibirsk said that the best database for JSON is Postgres. So I mean, in some way this confirms this claim. So next is Cockroach, but here, I mean, generally, like I said, resources for testing a single product are quite high. So you need to. We had a team which would pick one product at a time, which would try to tune it and so on. So with Cockroach, I cannot be as pessimistic. And this begins with just the first statement, and we'll see now the results with Yandex database that are quite similar, that some vendors, they don't recommend these tiny setups. So if you look at this, Cockroach says that you should start with at least 4 cores per shard, and we start with 1 core per shard. So maybe when you have high numbers, so if you just divide the entire space of like say NoSQL databases, I'd say some are focused on ingesting and handling more data, and probably large volumes of data, large chunks of data, and some are focused more on tiny transactions, tiny pieces, tiny queries. Like if you look at Redis, it really performs well with small like keys and values. And if you look at these vendors, they probably are focused on very large volumes of data, but not on high throughput. You know, so this is the impression that CockroachDB made on us. The numbers are not looking good either. So and you can see also that it's not scaling as we would expect it to. So you have more cores, more shards, and you have lower throughput. Now, and this is just the recent addition, and with it, I would like to wrap up, and you should not be surprised, exhilarated by the numbers here. So Yandex, we started testing Yandex database in March of this year, and we had, in the end of the test, we had full support of the Yandex team to run these tests. So essentially, the numbers I'm showing here to you are not our numbers, are the Yandex team numbers. And the interesting part of it, like I mentioned in the beginning of the talk, like at some point, databases to different directions. You know, there is this first branch, interactive transactions, and there is another branch where which is called predefined, pre-programmed transactions, non-interactive. We call them deterministic transactions. You would like when you have to specify the entire transaction body up front, this is what I call deterministic transactions. So it's not really fair to compare, say, Yandex with Postgres, because Yandex database doesn't support interactive transactions. So these are the numbers when you have to put entire transaction body up front. But unfortunately for our case, this is the case. So we know the transaction we are going to run. We can tell the database about it, and the transaction schedules are very different when you you don't have to support interactive transactions. So this is not a very fair comparison. Like Foundation and Cockroach and others, they do support interactive, and Mongo, they do support interactive transactions. So this is non-interactive. But the other part that's interesting about it is, like I said, these numbers is just the first numbers of a good result. Our results were also horrendous initially. So we would get a cluster of, on a similar cluster, if you look at this cluster is actually using much more hardware. So if you recalculate it, and I haven't done the job, like the numbers came out just this week. I haven't done the job of properly running it and recalculating this to transaction per shard, transaction per core, price metric. But if you just look at the sheer numbers of CPUs and RAM here, you will see that these are not impressive numbers. And if you look at this chart, you will also see that the rest of the vendors, we would run them in Kubernetes cloud, and this is not using Kubernetes. This is a bare metal setup. So why this? Why this? We know that, well, and I haven't seen that myself, but I can quite believe that Yandex database scales to millions of transactions per second. It all is a matter of like your target scenario. So like I said in the beginning, there are databases built for tiny, small writes, and there are databases which are built for really high scalability, high throughput, cloud databases. Yandex is an example of a cloud database, which is, you can see that it's CPU bound. It's even though we are just doing tiny transfers, it has a very high write load, like 60 megabytes per second. And sorry, these are Russian megabytes, but wherever. So, so why this? This is a phenomena called write amplification, right? So if you have even a tiny write, you still need to write a large chunk, a large block. And this is, so probably if your transactions are like multi-megabyte transactions, Yandex database is best for you because it's going to really scale well and fare well in this environment. If you have tiny transactions like financial transactions, you are still going to pay the cost. And I think it's a good example, it's a good illustration that all databases are different and built for different workloads, and you need to look at them like this is a good way to look at them to see. Network is also a telling thing, like 100 megabytes per second to run 50,000 writes. Like if you calculate the raw footprint of these 50,000 transactions, it's going to be probably in under a megabyte, generally. Like how much data you are actually changing, under a megabyte. And you run 100 megabytes per second on every node to maintain that. So with that, and I think I'm running out of time, no? More or less. Okay, but I'm running out of sticker. It just hung up. I need another sticker to. Do we have a replacement? Just not working. Can you switch the slide for me? Oh, yeah, it started working. Thanks. And I didn't say anything about chaos tests. So the last part I would like to mention is the chaos mesh, which I started with. So for these vendors, we would run also the chaos mesh tests. And you know why I have this funny guy against PostgreSQL? We had this funny conversation with Yandex at one of the conference when they would claim that, hey, PostgreSQL synchronous replication is just excellent, just works out of the box. Patroni is not something you should be using, but our Yandex replication for Postgres is just good. In the end of the conversation, it turned out that they don't open source it. So they're talking about some proprietary stuff they run in their cloud. Okay, I can't quite believe that Yandex and PostgreSQL, Postgres in Yandex cloud is quite good, and maybe Postgres in, say, Amazon cloud is quite good. What I am interested in, like I said, if you look at the premise, is that you can look at this research, is that you can run it on premise. So FoundationDB fared quite well. CockroachDB actually fared quite well. We ran some tests, but you know, they're not full, so this is why we're not mentioning it. And here again, Mongo, like why I'm showing it, this is not the full truth. So actually, if you properly configure Mongo, if you properly use Mongo, it passes the test. So let's just be, so what is the issue? Why did I put a cross against it here? First of all, you learn about it hard way. We spent a lot of time making sure Mongo doesn't lose data for us. So probably if you use Mongo Cloud, you're going to be fine. But so the key point for us was that you don't just need to use transactions. You also need to replicate with quorum to make sure you don't lose data. This wasn't like intuitive to us. Like I'm already using cross-shard transactions. Why do I need to have to do anything else? So write concern has to be set properly. Another thing to make sure that Mongo works is that when MongoDB has this timeout built into it, like it's called transaction total time something limit, which is by default put into 1 second. So it would just quietly roll back the transaction for you because it just runs for too long. And you have to adjust for it. Like one important thing every application writer has to keep in mind. When you switch from a vertically scaled database to a distributed database, you have to adjust your application to a whole new realm of errors which you need to know how to handle. And with MongoDB, it was exactly the case. So we would get some funny errors which we would not know how to deal with. They would abort our workers, and in the end, by the end of the test, all our workers would just die because they would get an error they cannot interpret, and they would just treat it as a consistency violation. So when we, with help of Percona, with help of just forums and everything like that, over a few months we learned what errors are actually fatal, what errors we can retry, what errors we need to assume that the transaction is actually committed. We managed to get the workload to pass in presence of the chaos mesh. So once again, when you compare databases, it's not about the numbers, not just about the performance. It's how much time you spend to just get familiar with it. And never, if you say to yourself, like, I am familiar with it, so this is not a cost for me. This is a lie, you know. So because there are going to be future generations which are going to come, so and they will have to deal with that. So to conclude, scaling transaction workloads is hard. You can always, complain about MongoDB. Nothing, you're not getting beaten for that. So it's always easy and safe. And yeah, so the tool is open. Everybody is welcome to try it. And my actually goal, like my tiny little plan, is that this creates some landscape for all vendors. Like Jepsen is there for consistency, and this is a measuring stick for throughput plus like availability and ease of use. So that's it. And thank you. And now to your questions.
Thank you, Konstantin. We have 5 minutes before we open the windows to let some fresh air in. So if you have a question, please raise your hand.
Yes, please.
Yes, we would be passing the microphone.
That there. Ah, you wanna
Yes, that's our friend from Yandex. You know how it's easy to distribute Yandex database in Armenia?
Yes.
Because it's YYYDB.
And he has a microphone.
Go ahead.
Thank you for perfect performance, and moreover for test suite. Just one thing to mention. You thought YDB doesn't support interactive transactions,
Yeah.
but it supports.
Yeah, so you
It can handle,
comparison.
run, and manage interaction transactions.
Okay.
Interactive transactions.
Okay, so I didn't know that. Okay, so
Thanks again.
yeah, let's go on with the question.
We have a question over here. So from a question from Yandex, we're going to a question from. Okay.
Hello, thank you. And what about ScyllaDB?
So Scylla. It's a. So you don't ask me what about Tarantul. That's interesting. So there, like if you look at vendors generally, there are databases which say, hey, this is our best niche. This is what we are built for. Like we deliver this feature. Neither Scylla nor Tarantul recommend this kind of thing. So even though Tarantul supports non-interactive transactions on a single node, and you can build a data pipeline. If actually, when we built a data pipeline for Tarantul, instead of using transactions, the data pipelines are hard to build. They're hard for engineers to grasp. So you can get much better numbers. And the same is true with Scylla. When the test is implemented for Scylla, you can go to my GitHub and you can get it and you can run it. The issue is Scylla never recommended lightweight transactions for scalability. And like I said in the beginning, you'll have to deal with so many exceptions which you handle on the client side. The structure of the transfer is going to be complicated. It's just not a competitor in this space. You know, it's just too complicated. So
Okay, thank you.
One more question.
no?
In this case, high-load Armenia merchandise goes to.
The only contender.
Yes. So let's just thank you for the question.
Thank you.
Because the first question was out of the question. It was just a great comment. So please rate the talk.
Thank you.
We use the ratings that you leave after the conference to make the next conferences better.
Yeah.
12:10. Kostya, don't leave.
No, I need to.
You need to bow. Thank you very much. So, Konstantin is not leaving. He's going to the discussion zone. You can chat with him a little bit. a little bit more and ask the questions that you don't ask using the microphone.